when we want to estimate, the pore pressure at the depth here, the pressure is acting on a point, right? Not on a plane. Stress it acts on a plane, so it has the direction, but stress, the pressure acts on a point. So pressure will be from everywhere. And we call it hydrostatic pressure. When you talk about the water pressure, it's a hydrostatic. Static means that the water doesn't move. And if there's a water flow, then it's going to be hydrodynamic pressure. But the hydrostatic pressure means that the water doesn't move, so that you can just simply calculate from the water density and the depth, water column height. This X. What about the horizontal stress? We've been talking about only the vertical stress here. And when we calculate the vertical stress, we only consider the soil or the water column above it, right? But when we start thinking about the horizontal stress, then we have to introduce some of the parameters. So this is what we are going to study today, how to calculate the horizontal stress. Horizontal stress has the same relation among the total stress and the pore pressure and the effective stress. For example, when we have the particles, we can simply calculate the vertical stress, and horizontal stress also has the total stress and the effective stress and the force. In case of pore pressure, because they act at the same magnitude to every direction, so the horizontal pressure, vertical pressure, or diagonal, it's going to be all the same, the magnitude. The stress, total stress, and the effective stress are different. About horizontal stress. When we have a soil mass with the vertical effective stress acting on it, we can also have horizontal stress, horizontal effective stress, sigma h prime. And when the soils are at rest, and this means, at rest means that the soil is steady, it's in a steady condition. In the force equilibrium state, we can express the horizontal effective stress in terms of the vertical stress and the coefficient K naught. Sigma and be careful, this is in effective stress term. It's not the total stress term. Here the K naught is defined as this K naught terminology is called as coefficient at rest means that the soil is in the force equilibrium, so it doesn't move. But there will be different K coefficient of the lateral pressure when soil moves to one direction and the other direction. So that's why we want to differentiate the conditions of the soils in this term at rest. Tae-Hyuk. Typically, the value is about 0.3 to 0.6. The coarse grain soil, and 4.5 to 2. Okay. So this is in the effective stress term. We can also look at the total stress term. And total stress, and you have sigma V and sigma H. So sigma H, the horizontal total stress is K times vertical total stress. And here, the vertical total stress is sigma V prime plus pore pressure. And the or sigma H is horizontal effective stress plus pore pressure, where we can use the sigma term. So we can simply look at the equation and knowing that the K is not the same with the K naught. Here the K is horizontal stress coefficient. How can you find the groundwater table location? Did I tell you before? So, for example, when you go outside of this building, you will find the location of the groundwater table because that is the necessary information when you calculate the effective stress, right? So, then what would you do? So, let's think about this ground. And at some depth, you have a groundwater table, which is unknown. When you drill an observation well, we're going to drill an observation well. Until you find the groundwater table. Then, you're digging up the hole. At some point, the water will flow into this observation well, so that it cannot be at equilibrium with the surrounding groundwater table height. Right? So simply you're gonna just measure the depth from the ground surface to the water surface of the well. Then that is going to the depth of the groundwater. So, and above this level is for this is unsaturated, or it could be perfectly dry, but degree of saturation will be less than 100%. And below this groundwater table, degree of saturation is 100%. So groundwater table is defined as groundwater table is defined as the steady state elevation of free water standing in excavated hole. So the pressure at the surface of the groundwater table, or right at the groundwater table, is equal to the atmospheric pressure. It's going to be 1 bar or 1 atm. And as you go deeper, the water pressure will increase proportional to the depth and the OW, the density of the water. Okay. So always here, the water pressure can be negative, and here water pressure is 0, and 0 means that the gauge pressure is the same with the air pressure in absolute term, but in relative term, water pressure is 0. And will increase to about time G and the depth. We have two particles, and you add some water to this dry soil, and the water will find the corner where they can reduce the surface area of the water. So this is the water. So interface between materials, in this case, the air and the water will be the two materials that act in each other. So in this case, the water and air will develop the surface tension of the water and forming the meniscus. So the reason they form the curvature, concave, is because the water likes to wet the grain. Okay? If the air was to wet the grain, then the curvature will be convex. It's going to be different. And here you have a surface tension at the meniscus that's pulling the particles into each other. So that increases the effective stress. Then to analyze this capillary force or the surface tension, we can use the tube analogy. This is much of soil. It is hypophilic. Which makes concave we're gonna use the glass as to represent the mineral. And the whole size of the soil is represented by tube and because of the small diameter of the glass tube, it's going to suck up and bring up the water. And here, to the tangent, to the contact between meniscus and the wall, we have a surface tension. angle between this is called alpha. Here, T is the surface tension. Water in air. Grass and water. In this case, the diameter will be D. And the height is called the capillary right, HC. So here we're going to divide the equation that can calculate the HC using the diameter and the surface tension parameters. Because these parameters T and alpha are known, and D will be also estimated from the soil side, so the HC is still unknown that we want to calculate. Okay, then start with the downward force. F down. Actually, this is the surface tension at the meniscus is in equilibrium with the weight of this soil, weight of this water column, right? So that the surface tension is bringing up the water by this much. So the downward force will be the weight of this water. So that's our weight. So the volume times load of the density and the presentation. So this will be HC times pi d square over 4 times load density. And the upward force that's bringing on the water is by the surface tension, this T. And the diameter is not diameter. The length of this circle times T is the force. Pi d from T cosine alpha. The reason that we are multiplying with the cosine alpha is that we want to separate the we want to extract the vertical term only from the T. So the summation of this force will be 0, down, F up, will be 0. Then MC down, F up. F down is the weight of water by this volume. Because without the surface tension, water level should be at here. Right? So by this much, the surface tension is holding the water more. It's the additional force. And that force is exerted by this T, by this surface tension. So the F down is the volume of water of this much times density and the gravitational acceleration, and the upward force is the surface tension times the length of the circle of the tube. Right? So Then if you simplify this equation, then you get HC as follows. So T cosine alpha over and this is called as capillary. So from this equation, if you know the diameter of the tube, which is the d here, and you know the surface tension, this is a kind of parameter, known parameter, will be given, and alpha is also will be given, and you can estimate how high the water can go up. So as the pore size or as the diameter of the tube decreases, as it becomes smaller, the line will be higher. Right? And you can calculate the pressure also. Capillary pressure is delta G and HC. So that's going to be simple. Some alpha over. And this is called capillary pressure. You can draw a pressure profile as the depth increases or the depth decreases. This is the surface of the water, so the pressure will be zero, right? At this point, pressure will be zero. And as you go deeper, it will increase by this much, right? Density times G times depth. And if you go up, it's going to be negative. So, to this height, this is HC, and this will be the capillary pressure you see. So here you get the compression, and you get the tension. Here is the compression. Here is the tension. Alpha is almost zero. So the cosine alpha will become identical. 1. So you can simplify more. The HC, capillary line, will be 4T over delta G. And capillary pressure will just 4T over D. Extension of the water.